our fourth webinar series for this year for the New Zealand Coastal Society. For those of you who don't know me, I am Rebecca and I am currently in the Young Professionals role on the Management Committee. So today we've got two great talks lined up. First up we'll have Scott Stevens giving a presentation on extreme storm tide and surge events around the New Zealand coastline. And then following him, we have Ryan Avery giving a talk on aerial drones and their applications for collecting coastal data. As Holly mentioned before, we will take questions at the end after both have presented. And just to make it a bit easier, if you could put the name of the person you're addressing the question to, that would be great for me. So yeah, thank you for dialing in, and I'll now hand over to Scott to introduce himself.
Hi Scott, sorry, it looks like your microphone has done what we didn't want it to do. So if you could just click disconnect microphone and just reconnect and just make sure it's selected on your headset. And if you just could turn your webcam on as well, that would be great. Thank you.
Okay, how's that? Can you hear me now?
Perfect, loud and clear. Thank you, and just your webcam. Cheers.
Okay. How do I do that?
Just the icon up the top next to the webcam, next to the microphone.
Yeah, no, it doesn't seem to be working. It's let's close that, and then I'll try it again. Okay,
No worries.
yeah, that's just
maybe
not
we'll
that's not working.
All
Okay,
right. Sorry
good as
about that,
gold.
everyone. I think we'll proceed without it.
Sure. Okay, well, hi everyone. My name's Scott Stevens, and I work at NIWA. I've been here a while doing coastal stuff, and the fun things I like to do when I have some time to do some research is look at the storm tides and our sea levels. And so I've done quite a lot of research over the years about the different components and joint probability analyses, etc., and helped apply those to map coastal hazards. But today I'm going to talk to you about some research we did looking at what makes up the largest sea levels that we experience around the coastline. And you might recall a couple of summers back we had a series of coastal flooding events which were driven by storms that happened to coincide with spring tides. So that's really to understand and manage risk exposure. Central government agencies, environmental emergency managers, and even the insurance and financial sectors, they all require knowledge of how likely, how frequent, and how big these events are going to be. And we, in this particular piece of research, we tried to take that a step further and look at the clustering of events in time and space and see what we could figure out was driving these events. So the way we did that was to start with was just to look at the available sea level records that we had and decompose them. And so we started with 30 sea level records that we cobbled together, and you can see straight away that there's some issues with the database, because we've got some that are very long records, sort of at the 4 main ports, and then some much shorter, but that's okay. The biggest event, possibly one of the biggest events in 1936, is not very well represented. Cyclone Bowler in '68 is not very well represented, but there was still a lot of useful stuff that we found as we studied it. These events now, An extreme sea level event consists of several components. So you've got the mean sea level, which is the average measured over some length of time, often several years to get a mean sea level, and of course that's changing with sea level rise. And then around that mean sea level we have what we call a mean sea level anomaly, which is just this variability month to month, driven by seasonal heating and cooling and climate variability like El Nino, La Nina, and then of course on top of that ride the tides, which happen to be the biggest source of variability in New Zealand. And then when you get storms pushing water on shore and the low pressure air pressure that storm surges are created, and you add all those things together, the storm surge and the high tide, and you get the storm tide. And on top of that we have waves as well that run in. Now this is some imagery of the 1936 storm tide, which was actually an ex-tropical cyclone that hit New Zealand. And that, up until 2011, that was the largest sea level measured at the Port of Auckland, which is our longest record. But in January 2011, it was exceeded. And both those events were about a 1% annual exceedance probability. In other words, a 1 in 100 year event. But of course there's a chance you get, as you know, that they can occur close together. And essentially they were similar in height, but mean sea level was about 12 centimetres higher than in 1936, which made that the largest event. But if it wasn't for mean sea level rise, then the 1936 event would have been the highest sea level record on record. So what we've done is we took those records, as I said, and we decomposed them into components. And one measure that we use, which is quite useful, is this thing called skew surge, which is basically the difference between the extreme sea level measured and the nearest high tide. And so what we did then is we do some joint probability extreme value analysis, and we combine those two together, and that predicts our extreme sea level curve. And we do that for the total sea level measured and also for the skew surge. And then we select the events that have greater than a 1 in 5 year average recurrence interval and analysed all of those events. So what we ended up with was we ended up analysing 85 distinct storm events that caused an extreme storm tide at one or more locations around the country, and 135 storm events that caused an extreme skew surge. And we're going to have a look at those events now. So here's an example of the breakdown at the Port of Auckland gauge. And so the top line is the very top line plotted there. That's the total water level, the ESL, extreme sea level. And so these are the largest 1, 2, 3, 4, 5, 6, or I don't know, about 25 events or so. And then the line below that is the height of the tide associated with those extreme events. And you can see on the right hand axis I've plotted some benchmarks. So the MHWS7, that's mean high water spring 7, that's the level exceeded only by the largest 7% of the tides. So immediately you can see that almost all of those extreme sea level events were also large spring tides. But you can also see one event which falls below. And if you look at the next line down, well, that's the skew surge being plotted. And so you can see that if we move from the small events on the right to the larger events on the left, we see that the skew surge generally is trending upwards. So for the biggest events, we have a larger skew surges, but still dependent on that tide being high. And the very largest skew surge plotted in these events here actually coincided with quite a low high tide, and so it only produced a moderate extreme sea level event. In actual fact, we find that only 21% of the extreme storm surge events led to extreme sea level events or were part of them. And then lastly, the lowest line of all, that mean sea level anomaly. I guess the key thing there is that is both positive and negative. So it goes, and it's roughly normally distributed about a mean of 0. But what you notice is that in all of these events, almost all of them, it's positive. And that's actually, it's quite, that was quite an interesting study, because it is an important secondary effect, and it really does tend to tip these events over into being extreme or not. Another interesting finding was that extreme sea level events are pretty much, to a good approximation, linearly related to the tide. So again, it just reinforces that importance of the high tides and the high tides play in these extreme events. You can get a big surge, but if it's not a high tide, you're not going to get an extreme sea level event. And then you'll see there's a group that falls above that, slightly above that line, and those are gauges located in the top ends of our estuaries. There's not many of those gauges, but it does show that topographic amplification and amplification of surge inside the estuaries, and so that's a topic that needs a little bit more research. So now, looking at the types of weather events that lead to the big skew surges, this weather map here shows from the 5th of January 2018, which caused a lot of flooding in the Thames area and around the country. Now, this is a blocking weather type event, because in a blocking event you get this this big anticyclone which will sit to the south or the east of New Zealand and hold up a small tight cyclone which spins up and intensifies, and so you can see that the track that event took. And the other key type of weather system which caused the extremes was a trough. And so a trough is basically a long extended low pressure system, and this is an event from ex-tropical cyclone Fehi, which really did a lot of damage around the Nelson area, and in fact lots of places in New Zealand. And you can see there that the track of that cyclone every 6 hours as we went down. And when we look at a spatial analysis, we're looking here at 30 events where an extreme sea level or skew surge occurred at least 3 different locations around the country. So we identified 2 categories of events, and the first of these at the top are the blocking high pressure systems, and we can see that they really affect the top of the country, the northeast coast of New Zealand in particular. Now the blue dots there are the blue circles are skew surge events, and the red ones are extreme sea level events. So again, you can see some events like that were extreme skew surge events, but didn't actually create extreme sea levels and total water levels, that is. And then the second type, the trough type, tends to be a little bit more prevalent, and that generates extreme sea levels throughout New Zealand, but particularly in the South Island and the west coast of the North Island. And if we look at the tracks, we find the green lines there being the blocking systems, and the red ones being the troughs, and tending to come in a little bit lower down. It's all a bit of a mess, but you can see the centres, you know, the blocking high pressure systems, the centres of the cyclone at peak sea level were just north of New Zealand, and for the troughs just down to the bottom of New Zealand. We looked at potential climate cycle links, and so we compared the top events with the Southern Oscillation Index and the Southern Annular Mode and a couple of others, and we just didn't find any relationship. So it's really, these events are driven more by random weather events, I guess is one way, a loose way to describe it. So what happens then when sea level goes up? Well, we're going to find that these impacts become worse. And this is from a recent study which was exploring the role of storm surge as a climate change impact. And the key, so this was did some climate change prediction modelling and then looked at how storm surges would change. And so the blue indicates lower storm surges in future, and the red indicates higher storm surges. So you can see on the left an RCP 4.5 and on the right RCP 8.5. And the key there is that a bit higher in the southwest and a bit lower up around the north. But quite small changes in the 50-year average recurrence interval storm surge height. But if we look at how sea level rise is impacting on the number of extreme events, it's quite interesting. So what I've plotted here, ignore that kind of lots of different lines here, but basically on this axis we've got the number of days per year of sea levels exceeding the 1 year average occurrence interval, and the base year for that is 1900. Okay, now the gauge record doesn't actually start until 1944, but we see already that by then, because sea level has been rising at about 20 centimetres per century, that we're starting to see more and more events. So each black dot indicates the number of days per year that the 1 year average occurrence interval sea level was exceeded, as if sea level had been when it was at 1900. So you can see that increase. And if we look at the projections, so we fit the sea level projections through that and then extend them out. This is the RCP 8.5 projection. So you know, and this is the RCP 2.6 projection. So eventually, that what was once a 1 year average occurrence sort of event will be occurring every day of the year, and in actual fact, you know, we're already getting a lot of these events, and I think probably that's impacting on some of those the Wellington South Coast exposure that we're seeing. Even though those are waves doing the impacting, that's at base sea level sets the platform for the attack there. So I guess the key takeaway messages are that most extreme sea levels were driven by moderate skew surges combined with high perigene spring tides, which supports the approach of forecasting those dates using the red alert tide calendar, because tides are forecastable. And I guess another thing that I didn't mention was that the potential for really large surges and really large tides, we virtually didn't see that. So in actual fact, we really haven't been hit by a big one yet, but the potential is there. Extreme events were more commonly impacted the northeast of the North Island during blocking weather types, and the South Island and west coast of the North Island during trough weather types. And the mean sea level normally is really important, and it tips the thing over. It's an important secondary effect, and I guess the sensitivity of the the extreme sea levels to that small amount of mean sea level adjustment does show the sensitivity that the number of the increasing frequency will have to rising sea levels. The frequency of coastal flooding is already increasing and will continue rising, and that the projected climate change effects on storm surge are minor. And therefore, the key takeaway message is that really it's sea level rise is the key thing that will drive coastal flooding into the future. So I think at this stage, I'm handing over to Ryan.
Thank you, Scott. I see my presentations come through. Hi, I am Ryan Avery. I am technically a recent import from South Africa. I've joined Stantec here in Wellington, and I'll just be going over some of the thoughts I had regarding using drones in the coastal zone that I came across while working on my master's thesis back in South Africa. I was doing it part-time while working for a coastal engineering company called PRDW. So what I'm planning to do is go through a bit of a safety moment, talk about the problem of my thesis, kind of go through how I measured currents using the drones and some of the results, and then what I really want to get in for this is just go through some notable aspects that I picked up, which will kind of jog everyone's inspiration for how you can use drones in the coastal zone. So to start off, one of the issues that I came up with quite quickly was when setting off my drone. It was of quite interest to the seagulls in the area. And there are a few close calls where the proximity alarm that was built in actually stopped my drone from flying. And so what I ended up doing was just to allow for all the seagulls to acclimatize themselves. Instead of flying around initially, I would just take off, sit about 10 meters above where I was on the beach side, and hover there, so that if one of the birds did come in contact with the drone, obviously the drone would just fall out the sky and would fall on the beach, not in the ocean. And what I found is they initially would be interested, fly around it a couple times, and then soon lose their interest after a couple seconds actually, and let them carry on. So yeah, that would then let me do what I was doing. But one thing that we also need to take into account when flying drones in the coastal zone is that you're also impacting these birds. And I know that one thing that is especially prominent in New Zealand is that the shorebirds, when they're nesting, they get frightened off thinking that your drone is a predator. So if you are planning to do some sort of drone inspection, just make sure to check the time of the year and that there aren't going to be any birds nesting at that point. And try and put some mitigation measures in place. See if you can do that a little bit later, or try and do it in another area where they aren't nesting at that point. And also remember, any time you use the drone, make sure that you follow the CAA rules. They're part 101. Just go and Google it, and you'll come up with what you need to take into account. So essentially what I did for my thesis was following on some work that one of my colleagues had done looking at currents at Monwabisi Beach in Cape Town. The beach had an artificial groin and a spur that they put in place to try and make the beach safer for swimmers. And what ended up happening is that it increased the currents, and this was quite a unsafe beach where a whole bunch of swimmers and fishermen had been washed out to sea and drowned. So there are a number of studies, one done by CSIR before this and then by Kistner, looking at the kind of mitigation measures that they could put in place, like extending the breakwater or changing the breakwater, just to try and see if they could reduce those currents. But one of the things that they weren't able to get was actual on-site calibration results. Obviously, if you're looking for something like that, you've got to deploy something like an ADCP, which is quite expensive to put in place, and you've got to leave it there for a couple of weeks and then get divers to either replace the batteries or You pull it out, and especially here where it's quite shallow, it doesn't work as well. Plus, it only measures a single location in space. Otherwise, you going back, you do something like the GPS drifter, which is there on the right, which you then again need a whole bunch of divers to employ. There are safety issues again, which goes to that, so it's not quite quick and easy. And especially when you're looking at right at the front of a project and you're wanting some initial data, you know, these kind of applications are not that easy to put in place. So in that case, I was looking at another way of getting some current data. What was proposed is that I would take a orange, throw it out into the bay, and then hover my drone on top, and then take photos of it after time. The reason I used oranges is because they're biodegradable. So if some of them floated away and couldn't be recovered, it's not that much of an issue. They would biodegrade anyway. Plus, an orange is obviously quite visible. So as you can see there, each one of those crosses is actually a location over time that you could then track in AutoCAD. I had quite a bit of a manual process where I would put all of the photos in AutoCAD coordinated using the drone's GPS and height to scale the image, and then use that to get the X and Y coordinates, which I could then get velocities from. I found that there were a few issues using the drone that I did. I had a more simpler Mavic Air, which was my personal drone to use. So therefore, there were some effects like the altitude of the drone, because it was using an onboard barometer. This had quite an impact depending on the actual height that it was. That gave a bit of an error. Plus, there was a bit of a GPS lag between when the photo was taken. So anytime that the drone moved quickly or rotated or something like that, you could end up with some serious errors, like is shown in that slide where they came up to like 5.6 meters. But if the drone was hovering in a specific location, it seemed like I got quite good results, and with some post-processing, I managed to make some good assumptions and got some good results that way. Funny enough, just to plug, I will go into more detail with that in the Water New Zealand conference. I'm giving a presentation on actually what I was doing there at that point. But for this, I'm going to focus on some of the other aspects. So if you're more interested in that, there will be a paper coming out on how I did that through Water New Zealand. Other things that I noticed is that the drifters actually ended up getting dragged along with surfing effects. So these photos are 2 seconds after each other, and you can see that if a wave comes along, the drifter could get pulled on quite quickly. One mitigation measure could be putting in a drogue underneath, which should hold it in place. I didn't explore this as I was looking for the more biodegradable and simpler option. But needless to say, you can see in the image on the left, I got quite a few results after time, which allowed me to estimate the current velocities within the bay. And comparing to Kistner's model study, I did get similar circular patterns, apart from a few locations like the middle where I think some surfing effects were in place. But essentially, it was a bit of a proof of concept that the drones could be used, and they were in the region of what Kistner was expecting. There should be a video that will play, but one of the future improvements that could be done would be to look at genetic algorithms or visual learning, which could then see these drifters moving in the water instead of using a AutoCAD click over time. I'm not quite sure if that video is playing. It actually seems to be struggling on my side. There you go. And then, so what's actually happened is here at Stantec, one of my colleagues took a look at this and managed to plot it over time as well. And that was quite useful. That will save a whole bunch of time and therefore make the process quite a bit more efficient. On top of that, some of the other aspects that could be picked up, let me see if I can close that, is you can actually see from above when the sediment is being stirred. So again, using genetic algorithms or visual learning, you should be able to pick up some of those movements and both estimate the currents as well as estimate some of the sediment transport within the bay, which I think is quite a useful application to not only calibrate some of the sediment transport models, but also get an idea as to where riptides are and those kind of things, because you will actually see where the sediment is moving over time. Another thing that I noted is that instead of using the oranges for drifters, you could just use some of the floating debris that's around there. Here you can see some, unfortunately, some plastic, as well as just floating kelp and those kind of things, and that could also be used if a visual learning algorithm could pick up these things over time and exclude some of the surfing effects going on over time, as well as when the conditions are right, you can actually see below the waves. Here you can see some of the reefs underneath. And I've also seen some studies recently where they've been looking at the refractive index of water and building that into photogrammetry, so that they can actually get seabed surface results from above using drones. So instead of going and getting soundings from underneath in some of the more shallow zones where you wouldn't be able to typically get a boat anyway, you can possibly get some seabed profiles using aerial imagery. Another aspect I noted actually at Monwabisi, there was a desalination brine outfall, and you could see the outfall from above. And using just manipulating the colors of these images you can actually extract some data. So by saying which light or intensity, you can start picking up concentrations from that, and with calibration you can estimate some of the concentration profiles to estimate what dilutions you're getting and those kind of things, which could then also be calibrated using on-site measurements, and see what your influence zone is around diffusers, as well as some discharge monitoring and those kind of aspects. Another thing as well is marine life. I had a few seals swim underneath me, and they're a school of fish. So a quick way of getting out and above marine life, obviously you want to stay far enough away that you're not stressing them out. But I've even seen studies where drones have been used to get mucus samples from whales flying through their blowholes where they're going through. So I think it's quite a good application where you don't actually have to drive a boat or get divers up close to marine life. Another thing that was picked up there in Monwabisi is algal blooms. This one was picked up because there was an issue with biofouling on the desalination screens. So this photo was actually taken up above the intake for the desalination plant. So there it was quite easy to see that there was a concentration of algae on top of that, and this could be used to keep track of the condition, plus also feedback to the desalination plant what the water quality could be. One of the things is if we had a few flights like this at the prelim stage, it would have impacted the design of the intake, and we probably would have pushed it a little bit further out to try and get away from the surface there. Also, shoreline monitoring studies. This I actually did just out of interest from the same location. I chucked a few images there on online application Maps Made Easy, which has a free use for a certain amount, and compiled a few of these images together to actually get quite a good composite image. And this also allowed for 3D, so as you can see here, you can actually fly around and rotate it and see what the shoreline looks like. You can get some contours, which you can pull out, as well as if you do this over time, you can use it for shoreline monitoring to track erosion and get a better idea of what's going on. And it's quite a quick way to do a large portion of coast at the same time, where you'd only need to fly, 2 or 3 routes on top of each section to get quite a good model, as long as you get enough overlap. And then finally, just a plug for New Zealand Coastal Society. If you saw the coastal news from a couple months ago, Tom Glauer and Tom Porter from Auckland and Patel Delamore, they did a bit of a study where they used the Splash drone, which is actually a waterproof drone, so it's quite applicable to the coastal zone, to actually get some water quality monitoring results by actually flying a drone out, and that thing that's held underneath with the string is actually, you can drop that down into the water out to get some water quality results, and that you can even weight so that it can take the measurement from different points in the water column, which is quite useful. And it saves having to get a boat and all of those kind of things as well. Plus, these drones can fly 1 kilometer or 2 out to sea, so they are quite useful. Obviously, making sure that you're flying within the rules and regulations. Sure, so that's it from me. I'll leave you with this quote from Albert Einstein, and we can move on to questions if there are any.
Cool, awesome. Thanks, Ryan. And thank you, Scott, as well, for presenting. So yeah, if anybody has any questions, feel free to put them in the question box there. But yeah, thank you both. They're both really interesting talks and applicable to some of the work that I do. So we have one question here for Scott. What was the range of sea level anomaly observed?
So the mean sea level anomaly is typically 0.1 plus 0.05, to 0.1, but some of the largest ones were actually around 0.25 up to 0.25 of a meter in places, rarely. So that's significant. And so the way we actually got that mean sea level anomaly is using a 30-day running average. So it'll be related to those seasonal impacts, but also wind, weather, weather patterns sort of really driving that stuff on shore.
I actually have a question for Scott there. You were talking about those two 1% exceedance storms that happened quite close to each other. Did you rerun the EVA after that, and what effect did that end up having on the EVA over time?
Yeah, that was probably my confusing presentation. The two events that I spoke about were the 1936 event and the 2011 event, so they were actually a long way apart. But the particular extreme value method we use is a joint probability method, so it's a lot more, it's less affected by those extreme outliers because it works with the combinations of the tides and then the skew surge and basically recombining them. So it's kind of robust to that. But if you've got a relatively short record and you're fitting a direct maximum method like a generalized extreme value, then they definitely start to pull up when you get a couple of closely spaced extreme events.
Cool. And we've got a question here for you, Ryan. Have you thought about the benefit of using the RTK eliminate the huge errors that you showed?
Yes, David. Actually, I did. Sorry, I was wanting to mention that is it came out kind of while I was busy with my masters anyway, but did mention it in the results. Didn't quite fit into my budget at the time. That's why I was using the smaller Mavic Air. But definitely going forward, something like the RTK, which relies a lot less on the barometer reading, would be beneficial in doing what I was doing there.
Cool. And a question for you, Scott. Does the vegetation change the effect of the flood, or is this an unknown variable?
So we didn't look at that in this study, but I do know that vegetation does damp flood waves. So some of the work Cara and Brian's been and Andrew Swales have been doing, and the measurements they have had out in the Firth of Thames during large storm surge events shows the role of the mangroves in damping the waves right out, and it also and the depth of that mangrove field also impacts on the surge wave as well. So it is quite a good natural, vegetation can offer natural coastal flood protection.
And so we've got a question here for you, Ryan. Would the use of, is it dollars? Have saved the road on the Coromandel, even if there was flooding? Not sure who, is this question directed to, might be directed to Scott actually. Either of you know?
Well, I mean, you can always put things, engineering solutions to, to prevent damage to infrastructure. That's one option, but we do know that that engineering solutions have a finite lifetime and they're expensive, so they need to be, put in with a view to the long term as well. So. Yeah, so probably location-specific DOLOS, definitely could have helped prevent damage. But if you're looking for long-term solutions as the sea level continues to rise well past what it is at the moment, then you need to ask the question whether that's feasible along long stretches of coastal roads, and whether there's other ways to adapt to that. And I guess the revisions to the coastal hazard guidance in 2017 proposed some a different framework for looking at that using dynamic adaptive planning pathways.
Cool. Another question for you, Scott, there. Did you find any correlation with the C anomaly or the IPO?
Yeah, great question. We haven't actually looked at that yet. So, but that's an astute question because that's the more likely to be the climate-driven part of things. So I've got a student with Karen, and he might get around to having a look at some of that stuff.
Cool, that'll be interesting. And we got another question here for you, Ryan. Can you use the NDVI sensors to identify the algae or other kind of element present in the water? And if yes, do you process and split the data between the organic material and water?
Yeah, as far as I'm aware, the NDVI is satellite-based, but it uses different spectrum of light. So, as you say, I think near infrared, NIR, I'm not quite familiar what the R is to that, but what you'd essentially say is that the algae will reflect a certain spectrum of light, and you can extract that light out of the image and see what area that would be compared to where the just plain water would reflect a different one, and you'd be able to extract the water out from that. And it's similar to saying, okay, the algae is green and the water is blue, but it would be a different spectrum of light, and the algae would be a specific section. So as far as I know, those image sensors actually use a different spectrum, than just light would, similar to how the infrared sensors do heat.
Cool. And so I've got a question for you, Ryan. When you mentioned about measuring the seabed with the aerial imagery, would that be pretty limited to the water clarity?
Obviously.
As far as New Zealand waters goes, it might.
Yeah, obviously you'd need to be able to see what you're measuring. I'm not quite sure how far those studies have gone. I just saw some initial testing that had been done, I think in the States, where they'd been using it to measure coral reefs, actually. So there you do rely on the water quality. But yeah, I'm not quite sure how that features into possible other spectrums of light or those kind of things. I guess all of these applications and everything are starting to develop now as people get more time to test and go through. And it just takes thinking a little bit out the box and trying new things to kind of do it.
Awesome. Well, does anybody else, we'll wait a minute or two if anybody has any other questions for either Ryan or Scott. You can send them through now. Just put a reminder out that, yeah, this is our final one of the webinars for this year, but we will be continuing this series next year. So I think we've got some lined up for January. If anybody, keep an eye out for there'll be a call for abstracts coming up. If you've got any interesting research projects or stuff that you want to present on, then make sure you get your abstracts in. I haven't seen any more questions come through yet.
Also remember we have the conference coming up.
Yeah, also. Yep, I was just about to remind everybody of that. Thanks, Ryan. I'm not sure, we did have a link earlier to the website, but yeah, all the conference information. So on the 26th of November, we have got slightly different format this year due to COVID, but I'm sure it'll be a great one. We've got a webinar which you can view online at home, or there is a number of locations where it will be streaming So we've got Auckland, Tauranga, Raglan, Wellington and Christchurch have set venues. And there will also be some social gatherings after there and a panel discussion being held in Tauranga. So that webinar is going to be based on the special publication which will be coming out soon, looking at the effects of sea level rise on our coastal systems. We've got the authors presenting on that work, and there will also be a young professionals lunch held beforehand. So this will be in Auckland, Raglan and Christchurch, and a great networking opportunity. I encourage all young professionals and students to go along if you can, if you're near those areas. Yeah, register online and it's free, so you can find out more at the link that's posted in the should be posted in the comments there. So yeah, thanks again, Scott and Ryan, for those great talks. Appreciate that, and appreciate everybody for dialing in. And we hope to see you all either online or in person
Thanks,
at
everyone.
the conference.
Yep, thank you very much.
Yeah. Cool.
Enjoy the rest of your
Have
day.
a great week. See ya.